I'm glad to be present here at this conference because the name International Scientific and Technical Conference is confirmed by my participation as a great guest from abroad. As I got the invitation, I decided to come because next year, next conference could be skipped, but this time I decided to come, and Sergei Leonidovich confirmed my participation. INFACON 2013, as you know, was a great forum for ferroalloy manufacturers from various countries, and the participants know Kazakhstan very well. In 2012, at the end of INFACON 2012 in Helsinki, we participated there for the first time as a member of organization committee, not as the delegates to the conference. And Sergei Yuryevich represented Ukraine. The member of the Academy of Science of Russia, Leontiev, represented Russia. And at the end of INFACON 2012, there was closed voting, and Brazil removed their candidates, and two Chinese companies were the candidates, despite the fact that Chinese was already the place for holding INFACON. And Professor Zhukov and Professor Leontiev was present at the 2012 INFACON, and the INFACON 2013 was held in Almaty. We were really glad. It was a very powerful forum for discussion. Such countries as RSA and Norway, they come as great delegations. There were about 450 delegates from 36 countries, and our countries were closed for the Western countries, but nonetheless they know these countries, our countries, very well. They had the possibility to visit Kazakhstan, some Kazakhstan and Ukrainian plants. And Norway and RSA representatives come with pleasure to our country because we organize social programs. The delegates come with friends and with wives. They can enjoy theaters or excursions, and at the end of any conference we have obligatory visit to a ferroalloy plant. There are some organizational moments with charter flights. We took our guests to Aktubinsk plant. In June, 4 furnaces, for high-power furnaces, are going to be started in June in this Aktubinsk plant, but still this shop is not in operation. But at that time there were lots of people, about 100 people, who wished to go to Aktubinsk plant ferroalloys. So at the end of the conference in 2013, I was really concerned about holding this conference, about various problems like charters, or about permission to come to the plant, but everything was well, and according to the results of the voting, the Chinese delegates and RSA delegates wanted to be the organizers of the next conference, and by the voting I failed to visit RSA, but RSA delegates all voted for Ukraine to be the place of the next conference. The committee decided that 3 years is too much, so the 2015 INFACON will be held in Ukraine as well. Ukraine is a great country. Kyiv is a very nice city. There are all the conditions for holding such an event. We've got lots of reports, and some of them were not on time, so we failed to process all the reports, and a part of these reports was left for INFACON 2014. So these are some reports that were not listened to in 2013. That's why we have such, in the interval 2 years, the people have to get prepared. And Mr. Barza accepted the place for holding INFACON 2013. Almaty, it's a historical moment for us. Our scientific institute worked on this project. You know that all the reports were accepted in English, but we made some exception because the translation services are very expensive abroad, and one day at one of the sections we allowed reports to be held in Russian. So our professors mostly study German language, and our professors had to report with translation. It was just one day. And what about sponsorship? Kazakhstan is developing in the ferroalloy industry. There are lots of new facilities, and Denmark became an exclusive Ferroplatinum sponsor. They are building a new shop in Aktubinsk. We've got a visit of Vice President of this company, and when he visited the fourth shop, he made a presentation, this Mr. Degil, and as everyone arrived to the airport in Aktubinsk, Degil bought beer for everyone, and he paid himself by his credit card. So we've got the experience of sponsorship, so to say. The organizer of Helsinki INFACON was Tech. We've occupied all nominations, got all medals, golden and silver medals. I think we won't have any bronze medals. Indian company became the bronze winner. All nominations were occupied by us. They have no problems. So I think that Kiev is a great place. Ukraine is a very important ferroalloy player. How that everything will be good, and all the materials were transferred. If some of them haven't been transferred yet, we will send them later, and we still have 1 year to come to prepare. If there are no questions about INFACON, I'll proceed to my report. All of you know very well that ferrosilicon alloy is not a new alloy. Ferrosilicon aluminium is produced by Kluchevsk plant by mixing liquid ferrosilicon with aluminium in scales, and China produces ferrosilicon aluminium. But when we say that we were the first to start the production of ferrosilicon aluminium, we are often opposed by our scientific colleagues. They say you are wrong. Kluchevsk and China produce such alloys 2 years ago. Mikhail Nikolaevich said that we produced such alloys in the Dnipro region with 65% aluminium. And some alloys comprised about 50% aluminium, 30% silicon. We produced these alloys from primary initial raw materials, and we developed the technology to produce ferrosilicon aluminium from carbonaceous ores by direct technology without use of coke. Carbon is used at nano levels, and we developed this technology. We have started this in the Soviet time and that of the 80s, and we tested these technologies in Ural aluminium plant, and in Akhtubinsk and in Yermakovsk ferroalloy plant in experimental furnace. And we also started experimental two-furnace plant for ferrosilicon aluminium with 1.2 megawatt-ampere power furnaces. The way was quite difficult because the high ash containing raw material is widely spread in Kazakhstan, in Sagadyrsky, for example, coal field. Complex alloys can be produced from quartzites. They have early fission, and all ferroalloy manufacturers know very well that the velocity of fusion will be higher than the reducing process, and everything will turn into slag, and any electrode will be able to improve this process. And the temperature of softening of this ash share is lower. So we melted ash, briquetted ash with coke. It's a SIP Electrostal in the Soviet Union, and we took this technology to ferroalloy plant, but the process failed. There was no contact with the carbon. Since 1998, we have studied all the carbonaceous rocks of Kazakhstan. Today in Kazakhstan, we have started in Karaganda the complex of alloys. The first furnace will have 25 or 33 megawatt-ampere power. And we have already started the construction of plant in Kazakhstan. The energy is not expensive in Kazakhstan. The first factor is the presence of very good coals, high ash containing coals, and cheap energy in Kyrgyzstan. In Kyrgyzstan, 1 kilowatt per hour costs 1 American cent. This is our dream. We can't have such prices here. And Mr. Zhamenov helped to promote this project to get international patents. This patent was bought by a Swiss company. It has an affiliate company in Germany, in Hanover. After this, ICMD got the exclusive right to produce ferrosilicon aluminum from carbonaceous rocks. It patented in most countries, including the USA and the European Union countries, Japan, China, Russia, Ukraine. I think is included. The next step, we produced the test batch of ferrosilicon aluminum. This test batch was sent to ThyssenKrupp, and the batch was tested, and this company bought the excluded right for marketing this alloy. This group failed to take advantage of the first ferrosilicon aluminum and ferrosilicon manganese. It was a new alloy at that time in the 60s. This alloy turned out to be very efficient, and every manufacturer now knows ferromanganese. So here, silicon and aluminium, that's what we develop now. And after CMD started the construction of a plant in Kyrgyzstan. In Kazakhstan, our colleagues started the campaign for construction of these plants for tests, and our opponents and somewhat consultants, Mr. Menshinin, they said that ferrosilicon Aluminium can be melted only in small furnaces with a small capacity, no more than 5 megawatt capacity furnaces. And this statement was checked at Pavlodar tractor plant. Now it's a steel production that produces pipes. The old furnace this furnace had the capacity 9 MVA.
So the same professional have said yes, but you need to use 9 MVA, not higher, because this process won't take place. So the German company buys this plant, n.a.Zh.Abishev, Estado do Brasil, and I participated in that Brazilian state. What state of Brazil is that? n.a.Zh.Abishev, which is a town 500 kilometers away from Sao Paulo, and n.a.Zh.Abishev sounds a tiny plant that has this is a small plant. Ferrosilicium 75 used to be produced here in Brazil, by the way, is the 5th largest economy in the world in terms of the speed of the development, and they have special low energy tariffs and no gas cleaning, and they have 5-6 years of gas cleaning benefits. And this is the plant producing ferrosilicium 75, and they use the wood coal, the eucalyptus. You got the tree and you have to plant another tree, and in 3 years this is going to be a full-fledged produce, and that is the wood coal produced out of there. No railways. The British bought the Portuguese built a railway that was disassembled, and now there are no railways. Only car transportation is the only means of communication. Quartzite, hematite, and wood coal, and this is what is used there. So we started to learn the coaly, ground coaly type. But you have the coals, you see the ashes, and then you have the coal. That's the layer over the coal 6474 and the volatile components, and you have the solid carbon. And from our experience, we can say that if you have 55-58% of ashes, this is the mono material. So we add additional quartzite, and the quartzite improves the process and increases the temperature of the melting of the material, of the charged materials. And we check out the ash component, and you see the first and second column for us is very important, because this is the we have the level should be 25 to 30%, which will provide to 15 to 20% of aluminum. Oxide of titanium is important. Oxide of titanium is something that you cannot do away without, because it's present in any type of coal. ThyssenKrupp produces a lot of cast steel where titan shouldn't be present. This is for deep extraction of steel, and they've asked us to. They say that we have 1 of 2% of titan and ferrosilicon aluminum. They've asked if it's possible to produce it free of titan, and it's impossible if we use the coal type, and this is going to be like the settlement technology, quartzite, bauxite, and coke. So we also studied, there are different types of coals, and that's the rigidity of coal once it's being grinded, and the trash material is typical 10 to 20 millimeter, and this is the output fraction of the coal is young. To make the fraction in ton of coal, you need to have 3 tons in the input, but these coal is stone coal, and the fine outcome is not big, only 3 to 5%, or even 5 to 10. And the raw material used for 1 ton of coal is, since we didn't have the right coal type with ashes of 55 to 58%, we used the highly ashed parts and low ashed type, and by mixing we have this type of charging material. So we have the coal type quartzite and iron turnings, and the chemical composition of this alloy that we were to obtain there, you can see it on the screen. The very plant is very nice and tidy and neat, and it has good plans for the future. This is a good ground for installing here 2 furnaces of 24 MVA that the Germans will do to produce not only ferrosilicon but also the it's very good to produce ferrosilicium magnesium. They add some manganese when produce. They decrease the temperature. Instead of 1 ton of ferrosilicium, they have 1.6 ton of ferrosilicium with magnesium, 6% of manganese, and the silicon is 50 to 60%. But this alloy is in high demand, and you can see. You can see the building with the furnace. So for some reason remote control doesn't function in my hands. The process transformation, this furnace was developed to produce ferrosilicium 75. So we're telling you if it's for ferric aluminum, the only furnaces that are good for crystallic silicon, but this is going to be a little bit expensive, and so these are the parameters that we've studied. They're good to produce the ferrosilicon aluminum that contains some silicon, 55%, aluminum is 15%. The next slide, please. And this is a very historical moment when they were launched in 2013, a new plant, but since the owner went bankrupt and he sort of took some of the finances in the offshore zones. Now the plant is being bought by the Swiss company ICMD. This plant is to be further increased and developed. This is the information that we were launching the furnace, the heating up, and with all the standard technologies. We use the coal type, the one that they got 73-75%, the coal of 77-28% of ashes. The mine is not near, it's kind of expensive to burn, although the electricity is not that expensive. And we use the quartzite. They both have quartz and quartzite and some other components, and the components of the mix was to obtain ferrosilicium 55A15. This is what I said, the average 55% of silicon and 50% of aluminum. The next slide, please. So the heating up pattern, heating up graph, and the next. So, and the dosage of the charged material, everything's good. The material is charged easily. The lowest temperature 50 degrees Celsius, but now they have the fall, this water, because the seasons are inverted in the southern hemisphere. In December it was summer in Brazil, and this is the charged material that we have. The coal type, coal quartzite, oxide part is almost 2 tons, and it's coke-free, as you see, and the component of the composition of the alloy, you may see it on the screen. And in August we since the factory hadn't been running for 1 year, and the average charge material wasn't an easy task at the beginning, so it was a little bit hard for us. The furnace, it all turned into slag in a furnace, and we had little metal output, and so we encountered carbide regime. And when you're using carbide regime, and by the way, this ferrous aluminum is very hard to be smelted. Slag and carbide regimes are visually look identical. Visually identical is very hard to decide from the other one, the carbide regime. the entire alloy once it's cooled down, turns into powder. Maybe somebody is making wire. This is going to be in demand for those who make wire, but powder produce is hard to be sold later on. And starting October 24th, we started importing some stuff and we started having 130% of melted stuff, and we're using those Brazil coaling type ones. We've studied the material 50. They place it a little bit earlier than we do it in Kazakhstan, and if you do it before time, you see that the furnace throat is very heated and it turns into liquid. And when we started adding special material, we see that the charged material wasn't melted before time and the process was stable. So we got the first silicium that contained 55 to 56% of silicon, and the amount of aluminum was just the right one as well. And this is the power that we've reached, but 7.5, that's the furnace output, and it produces 16 tons per day, and we consume 11,000 kilowatts of electricity per hour. So this is very extremely energy consuming process. And the silicon extraction 78 and aluminum 75, which is very good for this type of process. And this is the pouring facility, and the phosphorus content was not exceeding 0.003 because low phosphorus. But by the way, if you're going to use, we used to be melting using a Kibus's coal, the amount of phosphorus in coal 0.2, but Karaganda coal is 0.02, and you know that the phosphorus, when you're making ferrosilicium using the quartzite or shungits, you have phosphine, a gas which leads to the total disassemblage or ruining of this alloy. So we're observing this. Medvedev, when producing AMS using a Kibus's coal, because of phosphor, aluminum, argon, and silicon, when it was cooling down, it was turned into powder, just like cement fraction. And we got 110 tons on the task. The money was were given by German companies, so we lost a lot of finances because the coal was far away. We needed to bring it by trucks, and then we spent a lot of time. We had bad metal, not good quality metal, but 110 tons that they used. We got the results very good. The more components the alloy has, the better it is. And then we've been using aluminum, and because of this ferroalloy aluminum, its density is better than the slag. If slag is 3 and 8, 4.2 gram per cubic centimeter, aluminum density is 2.2, and for that you need to use special apparatus, special machines, trap machines. So the grinding, they do have the grinding, they can produce any fraction in that atmosphere. The also plant has it. So Brazil, just like India, lots of manual work is used, and when they were smelting ferrosilicium, that slag was melted by women who were sitting on the ground with tiny hammers, and they would extract the balls of metal, and then they break it into, and they would sell it to Thyssen Group. In this part of the world, the task, there are lots of populations, so they have to employ each and every one. They have to create additional working places. Okay, the next slide, please. And here we have the plant is fully equipped. The big bags and weighing and storages, warehouses, they do have it all.
Here is the ready-made product, as you see. Next slide, please. Next slide. And they have the laboratory fully equipped for chemical analysis. We could do everything on the spot. There were no problems. And we'd like to summarize. The Brazil coals are 50-70 degrees Celsius, have lower melting temperature. This has a negative effect on the technological process of smelting, but the results we have achieved witness that it is possible to produce ferrosilicon aluminum if the production is well organized and raw material comply with the standards. Next slide, please. As I have mentioned, these parameters that we have achieved, and the most important, the result was that the Germans wanted to construct the furnace with the capacity 20 megavolt ampere, and we proved that the more powerful the furnace is, as the disadvantage of our raw materials that the throat mass is charged. So this smaller furnace is the less load is on the charged material. So the furnaces have to be very powerful, about 25.2 megavolt ampere. So we will have the baking machines, and the charged material will be baked. And this process is extremely energy consuming, but the more powerful the furnace is, the less energy is lost. We can achieve energy saving and melt such alloys in the regions where the energy is not expensive, like in Brazil, for instance. So there are no, unfortunately, prospects for producing ferrosilicon aluminum in Brazil. They are going to produce ferrosilicon with low aluminum content, and Germans are going to buy ferrosilicon with 0.4 concentration with $200 bonus, and the prices for ferrosilicon are not going to be increased, but if ferrosilicon will have low content of aluminum, Germans are going to pay $200 to $150 bonus, and Brazils are going to produce ferrosilicon with some aluminum, low content of aluminum, but later they are going to produce ferrosilicon with the manganese. I have reached the end of my report. Are there any questions? I've got a suggestion.